Topic 4, and static forces. So for a while now, we've been talking about acceleration and velocity and motion in one dimension, motion in two dimensions, but we haven't really talked anything about what's causing motion. So this brings us to a fact of where we know about displacement, velocity, acceleration, but the cause of those things are going to get linked to forces. And if you ask a small child, how did something move, like a block, and on a table, and we might answer with the block was pushed or it was pulled. There are many mechanisms for pushes and pulls, but we group them under a general term called forces. So pushes and pulls. And some of these are contact forces, like a push, but there's other types of long-range forces, like gravity, the force of gravity. And this push-pull also has a direction associated with it. So that tells us that we're going to use, once again, vectors. And we use the same vector math for forces as we do with displacement and velocity that we've already become used to. They also could generally tell you the bigger something is, the harder it is to push. And if you want to make something move fast, you push it hard. So those sort of things could come from a small child. And this qualitative description really went on for quite a while. But Galileo started talking about measuring forces using calibrated coiled springs and double pan balances to quantify the inertia of objects or the mass of objects. So this led to Newton, who came up with 3 laws in there, and 4.1 is Newton's laws. So we're going to talk about those now. The first thing is, it goes back to the discussion of with the small child, okay? And so I really only need the one quadrant for this, the positive y and the positive x. We're not going to call it x. We're going to have x be x will be the force, and y will be acceleration. And if you applied a force here and had this acceleration to it, what do you think would happen if you doubled the force? Well, you would probably double the acceleration, okay? And if you tripled the force, you would triple the acceleration. So there's this relationship between acceleration and force, and acceleration is proportional to the force. This meaning proportional. Okay? Now let's talk about how heavy, or the mass actually, of something. So now on the x-axis, we'll have mass, and on the y-axis, we'll have acceleration still. Now, if you apply a constant force to a very large mass, let's say out here, well, the acceleration you would get would also be small. Okay? And And if you apply a smaller to the same force to a smaller mass, well, you're going to get more acceleration. And even smaller, even more acceleration. And that has a relationship like that. So in this case, the acceleration is proportional to 1 over the mass, because as the mass gets bigger, the acceleration gets smaller. Well, putting these two things together, we get the equation A equals F over m, where we have acceleration, force, and mass. And the acceleration is directly proportional to the force applied to an object and inversely proportional to its mass. Now, we usually can rearrange this to F equals ma, just bringing the m up, and in fact it's the sum of the forces that equals mass times acceleration. And we call this here the sum of the forces. It's also called total force, and you'll also hear it called net force. I tend to call it the net force. So, but it means the net sum of all forces on an object equals the mass of the object times its acceleration. And this is Newton's second law. We'll get to the first in a bit. And it just states that the acceleration of an object is directly proportional to the force applied and inversely proportional to the mass of the object. Good. Let's look at the units of force. Okay? Well, let's come back to this equation here. The sum of the forces equals mass times acceleration. Well, you know what the units of mass are, kilograms, and the units of acceleration were meters per second squared. So the units of force are kilograms times meters per second squared, but we also have an abbreviation for that, which is the Newton, N. So that's a Newton. So you might say the force applied is 3 newtons. Newton's first law. Newton's first law states that an object at rest or in motion at constant velocity will remain that way unless acted upon by an outside net force. So what that means is that you're in a state of what we call equilibrium. okay? And in that case, the sum of the forces is equal to 0. There's no net force. An object is in equilibrium. There is no net force. Equals no acceleration. So this can be with constant velocity, or it can be with zero velocity. In both cases, you have no acceleration, you have no net force. If you take like a table, and you have a box sitting on the table, well, there's a downward force from the Earth on it, but it's balanced exactly by the upward force from the table. And those forces cancel out so that the sum of the forces is equal to 0. We also have Newton's third law. And in Newton's third law states that forces are inherently plural. They are interactions between two objects. That every action has an equal and opposite reaction. So that the force of B equals minus Fa. In other words, if there's a force A, his hand pushes on wall, then FB is in the other direction, and it's the wall pushes on hand. You could only push on something as much as it's going to push back on you, because forces have to be paired together, and they are inherently plural. So if you try to push on a piece of paper with all your might, and the paper is free to move however, you're not going to be able to do that only as much as the paper is able to push back on you. Another example would be car hits bug. And the opposite would be bug hits car. Now, the bug has a small mass and feels a super large acceleration due to that force. The same force on the car, because the car has such a large mass, feels a very small acceleration. We could also think of this in terms of the surface of Earth and a person. Right? The Earth is being pulled down, or the person is being pulled down by the Earth, and there's a force of Earth on person. There's also a force of person on Earth. We know what the acceleration of the person is going to feel. We've been calculating it. The acceleration is minus 10 meters per second for every second. So let's see and calculate what the force would be. So the person falling, if we ignore air resistance, the sum of the forces will just be the mass times the acceleration, and that sum of the forces will be the mass of the person. Well, let's say it's a 50 kilogram person, times an acceleration of 10 meters per second squared, negative, would give us minus 500 newtons. Okay? So because it's equal and opposite, the force the Earth feels is 500 newtons up. Okay? And we could have the same equation. Mass times acceleration. The mass of the Earth is 6 times 10 to the 24 kilograms. So 500 newtons equals 6 times 10 to the 24 kilograms times A. So the acceleration the Earth will feel is 500 divided by 6 exponential to the 24, which is 8.3 times 10 to the minus 23 meters per second squared. So even if the only interaction was that falling person and the Earth is going to feel a very small, negligible acceleration. Of course, the net force on the Earth is not only that person. There's planes flying along, there's a giant sun, and things like that that play much more of a role than the person does falling. But just from this simple example, you can see that the 500 Newton force that is exerted on the person and the Earth causes a much larger acceleration for the smaller massed person compared to the huge, giant mass Earth. Very small acceleration.